here. There we go. I think we're live right now. All right. So folks, as I was telling you, my plan was to. So last time, my plan was to finish up with a couple of questions that show how to apply, the concept of definite integral, the oriented areas, how to apply that to calculate some areas without much of a need of a real calculation. So, a very hard calculation. But we ran into some problem last time. So I gave you an example, but then the next example wasn't working well, so the last 10 minutes we had that interruption because the internet collapsed here. Some things happened. We'll address that in this lesson. So in this lesson, what I'm gonna do, and I'm gonna pull this already. I'm going to do a couple of questions that are more suitable. So these are slightly better for the purposes that I wanted to highlight last time. So we're going to continue here, folks, with 4.2, the definite integral. And again, the goal of this lesson is not to do a lot of Riemann sums and stuff, but rather to explain you how the definite integral, the way we defined it last time, and I'm going to draw the picture here. So if you have a function like this, and let's say this is a point A, and this is a point B over here, and maybe this is a point C over here. So when you calculate the definite integral y equals f of x of this function, so the integral from a to b of f of x dx, so that will be, folks, if you remember, we said that last time, this would be the area from A to C above the graph, above the x-axis, and below the graph. So below the graph. So that will be the first part. So this part here that I'm going to color, let me color that with red. So this part here, and then minus. So minus, remember that minus, and I'm going to say underneath the area minus again here the area from C to B below the x-axis and above the graph of f of x. All right, so that first area, the first area minus the second area. So the one below is this one here. So this is an area, but we're gonna put that with a minus. So the first one is with a plus, and the second one is with a minus. So we subtract those two. So that is the definite integral, folks. Now this thing here is the thing that I wanted to highlight last time, and somehow, because of so there was a situation there, and we kind of got derailed a little bit, but that's okay. So we'll come back and we'll address that. So the problem that I want to do, and I thought this problem is better than the one we had last time, is number 33 here. So I'm going to do number 33 here. So let me change colors, okay, to black. So number 33 from section 4.2. And that problem is the following. So I'm going to try to sketch a graph that's more or less like the one in the book. But again, so don't expect me to make it, perfect, because, it's kind of hard to, oops. There's the y-axis and the x-axis here. There we go. So we got you got a straight line and go like that. Okay, so there we go. So let's try this. We got a straight line going like that. Then I got something. Oops, there we go. Okay, hang on a second, folks. All right. So there we go. So that, and we got a straight line going like that. And then we got something going down, so all the way down like this, something like this, and finally we got something going like that. All right, so these are the things here, folks. This is the graph that we are looking at in the book. And in the book, it tells us, and this is important, it tells us that this here is at 2, and this here is at 3. Again, my scale is not perfect, folks. Okay, there's 4, there's 5 here. All right, so there's 5 here. The next one is at, this here is 7. And the next one, last one is 9. All right, okay, so these are the things that are of interest, immediate interest for us. This here is 1, there's 2, there's over here is 3, the level of this is 3. All right, then we can see that in the book. And finally, okay, I'm gonna say what this one is. All right, so this one here is, okay, 1, 2, 3, -3. So, I apologize. It's not well scaled, but you get the idea. So the problem here in the book says, folks, calculate the following things. So for part A, the integral from 0 to 2 of f of x dx. And we're going to calculate that. So that's our first goal here. So now when I calculate the integral from 0 to 2, folks, I have to be careful here. So what I mean is, because I'm only concerned about this part of a graph, which I'm going to draw with blue right now, this part of a graph, so this part here, right? 0 to 2 on the x-axis. It means that I'm interested in this area. That's the only thing that I'm interested in. And that area would be the area of a trapezoid all the way above the x-axis below that graph, the area of a trapezoid below that thing. So that turns out to be, the trapezoid can be broken down in a square, no, not a square, a rectangle. This one down here, 0 to 1 in height, the one that I'm going to make thick right now, this rectangle. So this one has a height of 1 and a base of 2. So that's going to be, the result of the area is going to be 2, that rectangle, plus the triangle that has a base of 2 and a height of from 1 to 3 is also 2. So the triangle would be the one just above it. So that's going to be plus, and that's going to be, because the triangle has a base of 2 and a height of 2, the area will be 2 times 2 divided by 2. So that's base times height divided by 2. So that's going to be 2. All right, so this whole thing is going to be 4. This is the answer to part A. Let's write again with black. So the next thing he says here, the integral from 0 to 5 of f of x dx. And this is going to be equal to, all right, so now we continue with this calculation. So we already broke it up from 0 to 2. From 0 to 5, we just have to make a look at a bigger area. So a bigger area here is this one. That's what's not counted the first time around. But this is, as you can see, if you look here, that's a rectangle of base 1 and of height 3. So to the previous area, which we already calculated, which was 4, we add up 3 from the rectangle, right? So this is the trapezoid. This is the rectangle here. And finally, this area from 3 to 5 and 3 to 3. So this is a triangle of base 2 and height 3. So that's going to be plus 3 times 2 over 2. So that's going to be plus another 3. So altogether, if you add up these things, the area will be 7 plus 3, and that's going to end up equal to 10. That is the area, the integral from 0 to 5. Part C, the integral from it says here from 5 to 7. All right, when we do the integral from 5 to 7 of f of x dx, let me color that with red. So we're looking at this part here. So the graph goes below the x-axis and the area, remember, the area is with minus here this time around. So we're going to say negative, and we're going to take the area of this triangle that has a height of 3 and a base of 2, this one from 5 to 7, right? That's a base of a triangle, the one I drew in red. And this is going to be, folks, equal to 3 times 2 over 2. So that's going to be the area is going to be, folks, equal to negative. So it's 3 times over 2, negative 3. So this is going to be the area for this one down here. All right, and finally, part D of our problem says do the integral from, okay, part D, 0 to 9 of f of x dx. And this is kind of nice. So this is where we got to be a little more careful. So, of course, what's left here for us, folks, is, let me change colors here a little bit. So we need to take into account this one. Now, remember, this is from 0 all the way to 9. So we need to be careful. So we need to take areas above and below the x-axis. So, but the one that's left to us and the one we didn't take into account is this one, this trapezoid, which is, this triangle that I'm going to make thick here. It has a base of 2 and a height of, let me see, I forgot to check what is this point. Oh, this is the point 9 comma 2 over here on the graph in the book. So it has a height of 1 and a base of 2. So the area of this triangle is going to be 1. And the area of the rectangle underneath is 2 times 1, so it's going to be 2. So altogether, this area is going to be, so we're going to say we just calculated from 0 to 5 in part B. So we calculated from 0 to 5. That's the one above the x-axis, so that's going to be 10. And then minus, and we're going to subtract the red one, which is already calculated minus 3 earlier at C, and then minus, and we have minus over here 1 plus this area of 2 is going to be minus another 3. So altogether, this is going to be 10 minus 3 minus 3. Again, remember, this is 1 here, and this one here is 2. But they're with negative signs, both of them. So minus 1 and minus 2. So that's going to be 10 minus 3 minus 3. And that's going to end up being 4. So you see, the integral from 0 to 9 turns out to be 4. So basically, folks, what we can see here is that some of the areas, sort of cancel out. And we end up getting, the 4 here for the final result. All right, so if you have any questions, do let me know. I think this is a very illustrative problem where we don't have to put our hands on any sort of Riemann sums or anything. We're just doing simple calculations with, rectangles and triangles and such. All right, things that we learned in high school. So it's nothing more than that. So I'm gonna change pages. If you have any questions, again, do let me know. I'm going to change pages. And I'm going to do another example. This is going to be number 34. And then we're going to do the fundamental theorem of calculus I told you. So number 34 over here from section 4.2 is, the same type of problem. So I'm going to sketch the graph here again, like I did earlier, using some, all right, so let's use the straight line tool here from Zoom. Okay, so we got that. And what else do we have? We have one from 4 to 2. Something like that. And then we have one from something like this. I don't know. So it's a small thing just going up like this. All right. So this is that, and then we have a what is this? A semicircle, which I'll approximately draw like this. So this is my graph, folks, for this particular function. This is x. The numbers here are 2, 4 is in the center here. That's 6, and this one here is 7. So again, it's not perfectly scaled, but you get the idea. So this is 4. All right, this is the graph of my function y equals f of x. Y equals actually g of x. I apologize, I got the wrong letter. So y equals g of x, different letter, but you know, you get the idea. So the first question is here: find the integral from 0 to 2 g of x dx. By the way, folks, you've noticed in my lessons, I always read the integral from the lower number to the higher number. In other words, from left to right. There's people out there who read the exact same integral, the integral from 2 to 0. In my opinion, that's not a good way to do business. But you know, it's a matter of taste in the end. So I will keep reading the integrals from 0 to 2. You know, the lower number first and the higher number next. But you know, again, it's up to you. I'm not going to consider that a mistake if you read it the other way around. Just know what people mean when they read the integral properly. So that means to me, folks, the area under the graph of g or above. Let's see where g is from 0 to 2. G is this line here. So there we go. There's that. And that is the area, so that I want to calculate, and it's very simple. 4 times 2 over 2, so that's going to be an area of 4. It's that simple, folks, by inspection, literally. All right, part B. Integral from 2 to 6 of g of x dx. Let's see, where are we with this integral? Okay, so I'm here with a red thing. So 2 to 6, this is my graph, right? So 2 to 6. Can you tell me here, what is this area over here? So, the area is going to be, folks, is going to be the area above this half circle over here, and that's going to give us you know, so below the diameter, so that's going to give us the area of half a circle, right? Now you know that the area of a circle is pi r squared. Remember, folks, pi r squared. The radius in this case is 2, half of the diameter. So so the area of a full circle would be pi times 4. But you know, we're talking about half a circle, so half of that will be pi times 2. So so the area here is going to be 2 pi. Again, it's a little confusing. It's also the same as a I'm not going to comment on that. So so anyway, so pi r squared divided by 2. Let me actually say that. That's better. So pi times 2 squared divided by 2, and that's going to end up being 2 pi. There we go. So that's more of a that's more fair to the answer. So all right, and we have to remember to get the negative sign here. Oh, that's that's the important thing that I forgot. So so negative sign here. So negative 2 pi, it's a negative thing. So so negative here as well. All right, folks, so that's part B. And finally, part C. And all right, again here, so part C, integral from 0 to 7 g of x dx. So what is this going to be? Well, so let's see what we have. From 0 to 7, 0 is here, by the way. 0 to 7 means this one with a plus, this one with a minus, and finally this small piece here with a plus sign. So the integral will be 4 from part A minus 2 pi from part B plus this triangle here above the x-axis, which is height of 1, base of 1, and that's going to be That's going to be, folks, 1 times 1 over 2, so it's going to be plus 1/2. So the area will be 4.5 minus 2 pi or something like that, if you want to write 9/2 minus 2 pi or something like that. So that's going to be the area, folks. The integral from 0 to 7. Again, we're looking at signed area. So the one above with a plus, the one below with a minus, again, the one above with a plus. And that finishes up our discussion here on, so this is as much as I wanted to discuss on this lesson in terms of, how to calculate area just by inspection, by using the definition. And I think this is important. So this makes up for what I essentially messed up last time in the last 10 minutes. I'm glad we got to do this again, and I think we clarified things here. So the next thing that I'm gonna do is I'm gonna move on, and I'm gonna discuss a new topic here, and that's gonna be the fundamental theorem of calculus. So section 4.3, and I said that this is a really very important section. The fundamental, why is it not letting me see that? Okay, so 1 second, folks. I'll have to delete this because it doesn't let me write here for whatever reason. So I'm going to write underneath here. There we go. The fundamental theorem of calculus. And this is lesson, as I said, lesson 4.3. All right, so there we go. There's two approaches to the fundamental theorem of calculus, and one of them is with the way they start in the book. They start with an abstract approach, and then they derive a simple thing. I'm going to do it the exact opposite way. So that's why I wanted you to all be here and pay attention to this thing, because it's very important to see how this is done. Again, so what do we need to do here? So we need to, so I will need to explain you how to calculate the integral from a to b of f of x dx. So I'm going to start with that, and I'm going to explain you how to calculate this in simple terms. So the fundamental theorem of calculus says that if you somehow are able to find an uppercase f function, which is an antiderivative of lowercase f, the fundamental theorem of calculus says that all you have to do is calculate f at b, capital F, this antiderivative, evaluate that at b, and then evaluate it at a and subtract the results. So it's that simple. And you get your calculation. You don't have to worry about the areas. You don't have to worry about Riemann sums. You don't have to worry about anything complex. Now, to prove his theorem, so that was one of the key things that Riemann did. He proved that this is true. That was major in the development of calculus. Again, with this thing, you have a very flexible, very simple tool to calculate every single integral that you can think of out there. So you don't have to go through the pain of Riemann sums and not even areas and stuff like that. In case you have formulas, in case you can, because sometimes it's not possible to find the antiderivative easily. But most of the time it is. So this will do the job. Now here's some comments. As you remember, when we discussed antiderivatives, we said that we can, we can choose another antiderivative. Say instead of this f, we can choose some f plus some constant c. Would that make a difference? It wouldn't make a difference, and here's why. When you subtract here, if you do f of b, so this function evaluated at c, at b, I'm sorry. Yes, c is a constant, by the way. Say here. So if you evaluate this function at b, at lowercase b, then you will get f of b plus lowercase c minus, and then if you evaluate it at a, you would get f of a plus lowercase c. And when you subtract these two, you will see that the c's cancel out, so you still get f of v minus f of a, the one you had earlier. So basically, folks, what we're saying here, and this is why I told you it's not so essential in calculus 1 to worry about that constant c when you calculate antiderivatives. Remember, we calculated antiderivative a week ago, derivatives. It's not so important to figure out the constant c, because most of the time, and in particular in the fundamental theorem of calculus, in Calc 1, you never use it. So you could just choose your own antiderivative of the many possible there, and do the subtraction. So do f of v minus f of a, and you're all set. And as an example, so we're going to do examples of how to apply this theorem to various practical problems. As an example, I'm going to go back and I'm going to do that problem earlier that we did last time. Number 21. So we'll do number 21 from section, we're going to go back to one section to section 4.2. And remember that the problem we did there was this one, was the integral from 2 to 5. Watch my earlier video from the previous lesson. So integral from 2 to 5, 4 minus 2x dx. So just as a review, actually you don't necessarily have to watch it because I'm going to do it here quickly. So last time we said, you know, we're gonna sketch this thing. We're gonna figure out the function f of x here is 4 minus 2x. We're gonna figure out the graph of this function. At 2, we saw that the function was 0. So because 4 minus 2 times 2 is 0. And at 5, we saw that the function was 4 minus 2 times 5, 4 minus 10, which is negative 6. So we found out that our function had a graph like this. And it was going through these points, 5 and negative 6, and 2 and 0. So this area over here, we calculated easily because it was a height of 6 and a base of 3. So the area turns out to be 9. And I said negative 9 because of the minus sign. So we know that this is negative 9. But that's not the point. So right now, this was how we did it last time. The point here is to do it with the fundamental theorem of calculus. So now I'm going to take a look at this function, f of x equals 4 minus 2x, and I'm going to find an antiderivative. An antiderivative, I'm going to call that capital F, will be given by the formula. So the antiderivative of 4 here, folks, is 4x, right? And the antiderivative of 2x is x squared, so minus x squared. So this is going to be the antiderivative. What I need to do to calculate, you know, the integral from 2 to 5 of 4 minus 2x dx is to evaluate this antiderivative at 5 and then at 2 and subtract the result. So this is going to be 4 times 5 minus 5 squared, and minus, and then 4 times 2. Remember, we evaluate this f. So this is the one that we evaluate. This is f of 5, folks. And this is f of 2 here. So let me just mention so that everybody can follow here. So f of 2 is 4 times 2 minus 2 squared. And that's going to be 20 minus 25 here. So that's going to be negative 5, first one. And then minus, and over here 4 times 2 minus 4 is going to be 8 minus 4 minus 4. So so this is going to be negative 9. And there we go. We retrieved the answer that we got earlier. So we got the exact same answer in 2 ways. Now, you might say maybe it was easier to do it this way because the first way we did it last time. Because if you just look at the graph here, it's obvious it's a triangle. Just you know, apply high school math. And well, in this case, it's true, but I don't think it's too complex to do it with the antiderivative and the fundamental theorem of calculus. But still, you know, you have to go through these extra calculations here. So that will be very different from the case when, folks, you take some more complex graphs. So this is a really simple graph. And of course, it's very easy to apply the fundamental theorem of, to apply high school math. In fact, I'm going to go and I'm going to do an even easier one. And then we'll do a slightly more complex problem. So then we're going to go and do numbers 22 and 23, the ones that we were trying last time, and then yeah, so so it got mixed up there. All right, so another example that's very valuable. So when you have a constant function, so let's say integral from 2 to 5, I got stuck in 2 and 5. Well, it could be any numbers here of let's say 3 dx. What is going on here? So what's going on here, folks? This is 2. Let's say this is 5, and this is the function, constant function 3, whose graph is that is a straight line, right? Straight horizontal straight line. So 3 over here. So the area under the graph is simply this rectangle. So that's going to be 3 times 5 minus 2, right, folks? The area of the length of the base is that. So so it's going to end up being 3 times 3, and that's going to be 9 as well. Okay. Like in the previous problem, there's somehow an accident here, so I didn't intentionally do that. But you can do this with the fundamental theorem of calculus. If you remember that the function f of x equals 3 has an antiderivative, which is called f of, let's call it f of x, capital F of x, and that's simply 3x, right? This is the antiderivative. And when we calculate integral from 2 to 5 of f of x dx equals, integral from 2 to 5 of f of x 3 dx, right, folks? And which is 3x, okay, which is, and I'm gonna, oops, I was about to tell you the wrong thing, not the wrong thing, but it's coming up in a future lesson. So which is f of x, which is this one, capital F, 3x evaluated at 5. So that's going to be 3 times 5, f of 5, right, capital F of 5. 3 times 5 minus 3 times 2, that's f evaluated at 2, and that's going to be 15 minus 6, and that's going to end up being 9. There we go. So remember, folks, you can do these kind of calculations when you have either a constant here, 3, like it is in this case, or a linear function here to be evaluated, the integral to be evaluated. However, when you get something more complex, and this is one of the last problems that I'm going to do here, we'll do 2 more problems and we'll be done. Something more complex like number 22 of section 1.4, of section number 4.2, I'm sorry. All right, so number 22 says, do the integral from 1 to 4 of x squared minus 4x plus 2 dx. So last time I was about to tell you, well, here we can do this, and we could do this with Riemann sum, so I was, that wasn't a very good idea. So let's do it with the fundamental theorem of calculus. By the way, the fundamental theorem of calculus in many books, you will see it shortly written like this, FTC. Yep. F of x, my function is x squared minus 4x plus 2. Capital F, the antiderivative of lowercase f is 1/3 x cubed minus 2x squared, right? Minus 4 times the antiderivative of x, which is 1/2 x squared, plus 2x. This is an antiderivative. Remember, I don't have to worry about a constant c, just one antiderivative at my choice, and this is the one we have to evaluate from 1 to 4. So when we calculate here, we're going to say f of 4 minus f of 1. And this really is equal to f of 4 is 1/3 4 cubed, minus 2 times 4 squared plus 2 times 4. Okay. Minus f of 1 is 1/3 times 1 cubed minus 2 times 1 squared plus 2 times 1. All right, so we just have to evaluate these things at this function f at 4 and 1. And when we calculate, this is going to be a bit of a calculation. So 4 cubed is, boy, so, okay, so, okay. So it is going to be, okay, so 64. Okay, so 64 over 3 over here minus 2 times 16 minus 32 plus 8. All right, minus, and then we evaluate the remaining part, which is 1/3 here, minus 2 plus 2. Now, very luckily, these two will cancel out. So we really have, for the answer, okay, so let's see, what's 64 over 3? 64 over 3, folks, is, let's see, 60 over 3 is 20. So this number here, instead of this number here, which I don't like to erase like that, there we go. Instead of 64 over 3, I'm going to say 63 over 3, which is 21 and 1/3. Minus 32 plus 8 is going to be, minus 24. All right, and then we have minus 1/3 from here. So the 1/3s cancel out, and this is going to be 21 minus 24, and that's going to end up being -3 for the answer for this particular problem. All right, and that's calculating as the one of the areas that we left unanswered last time. And finally, one more problem, and I'll be done here, folks. The last problem that I'm going to do here is number 23 from section 4.2. And again, that's a problem we started last time one way and decided to go a different way. No, 25 we did last time. I'm going to do 23 here. Same type of problem. So integral from -2 to 0 x squared plus x dx. Same story. So we're going to call the function inside the one between before dx here, we're going to call it f x squared plus x. By the way, folks, I forgot to mention, actually I mentioned that last time, but these symbols, the integral symbol means, so the history is that Riemann used sums and he used the letter S, but the letter S was taken, so he came up with this idea of kind of making an elongated S, and that's how the integral appeared. Dx has to do with the fact that when you do, those sums, you do differences on the x-axis. You have the rectangles, and there's a height times the dx, the difference. That's kind of a historical relic. Some people simply write integral from -2 to 0 of x squared plus x and don't even write this dx here because it could be confusing. So this is the function. The antiderivative of lowercase f is this one, f of x equal to, so I'm going to say here 1/3 x cubed plus 1/2 x squared, right? That's a good one. And we are going to evaluate, so when we do the integral from -2 to 0 of x squared plus x dx, all we have to do is to evaluate this one function at the number 0 and -2. Now, when I put 0 in here, I get 1/3 times 0 cubed plus 1/2 times 0 squared. And then minus, and then I have 1/3 times -2 cubed plus 1/2 times -2 squared. All right, so this is 0 minus, And then over here, we have 1/3 times negative 2 cubed. Well, that's going to be negative 8/3. And then 1/2 times negative 2 squared will be 4/2. So plus 2. And that's going to be equal to, and that's going to be equal to negative, and negative 8/3 plus 2 is going to be negative, all right, that's negative here in front already, right? And then parentheses, negative 2/3. So altogether, this is going to end up being positive 2/3, the result of the integral. So that is going to be the answer over here. All right, folks. So this is where I am going to finish the recording today. If you have any questions,